now.
Hello, everyone. Welcome to another venue for our high-energy astrophysics division seminars. Today we have a very exciting lining up of 4 speakers under the overarching title of the Particle Background and Transient Study in preparation for Athena WFI, Wide Field Imager. So our speakers are Eric Miller from MIT, Gerrit Schellenberger from our own CFA, then Wilkins from Stanford, and Amanpreet Kaur from Penn State. So let me give you a short introduction to each of those speakers in the order I've just said. So Eric Miller is a research scientist in the MIT Kavli Institute, where he studies diffuse material in and around galaxies, focusing on the outskirts of galaxy clusters and the warm-hot intergalactic medium. He works to develop next generation of X-ray imaging detector, and he's also detector lead of AXIS, an X-ray imaging mission concept awarded by NASA. And he's also involved as a detector instrument scientist in ARCOS. He's also detector lead for a series of soft X-ray polarimetry mission concepts like Red SOX and PI SOX. He's also leading the in-flight calibration planning for XRISM, heading about 30 plus scientists and instrumentation experts. And as a member of Chandra and Suzaku Hitomi science instrument teams, he has an extensive experience with calibration and development of X-rays CCDs. He's also a member of the Athena WFI Background Working Group with experience in modeling the background of space-based X-ray imaging detectors. Okay, the second one, Gerrit Schellenberger, earned his PhD in 2016 at University of Bonn, Argenlander Institute for Astronomy. Between 2016 and 2021, he was postdoc at CFA, working with Jan Vlitlek, Larry David, Ewan O'Sullivan, Bill Foreman, and Christine Jones on multi-wavelength observations of galaxy groups and clusters. Since 2021, he's astrophysicist at the Smithsonian Astrophysical Observatory, working with Ralph Kraft, Paul Nalsel on investigation of background reduction algorithm for Athena WFI. He's currently active collaborator for Athena Heritage, which is an XMM Newton program to observe Planck galaxy clusters and map their outskirts, and other missions. Our third speaker is Dan Wilkins, who is a research scientist at the Kavli Institute for Particle Astrophysics and Cosmology at Stanford University. He received his PhD in astronomy at the University of Cambridge in 2009. And after a short research fellowship in Halifax, Nova Scotia, he was Einstein Fellow at Stanford. His research focuses on supermassive black holes at the center of galaxies, how matter plunging into them powers some of the most extreme objects that we see in the universe. His pioneer studies on the X-rays that reflect and reverberate off of the material falling into the black hole to map out the extreme environment just outside the event horizon. And alongside the research in supermassive black holes, is working towards development of some of the next generation of space-based X-ray observatories. Last but not least, Mapreet Kaur, who is currently assistant research professor at Penn State University, working primarily on blazars and Fermi and associated sources with machine learning methods with Professor Abdi Falcone. He obtained the doctorate at Clemson University, working with Professor Dieter Hartmann on probing bulge to disk nova ratio in M31 in 2016. This was followed by the postdoc appointment for 2 years until 2018 with Dr. Marco Aiello at Clemson University, working on obtaining photometric redshift of BLX using Swift and various optical telescopes. He then joined the PSU as a postdoc in 2018 and was promoted to the current position in 2019. In the last 2-3 months, he started working on transient and neutrino emission from blazars using Athena WFI, and this will be the topic of the presentation today. So just as a short reminder, since we have many speakers today, we proceed this way. We'll just let speakers speak one after the other without interruption, but you can still put your questions in the chat. They will be answered by the speakers as the talk goes on, or in the chat, or at the end, if some of them remain unanswered. And of course, you can ask them at the end of the talk as well. Okay, so after all this long presentation, please, Eric, the floor is yours.
All right, great. Thank you very much for the introduction. And thank you for inviting the four of us to come and speak to you today about some work we've been doing for the Athena WFI, in particular, understanding the particle background and preparing for transient studies. So I think most of the people who are listening know about Athena. Athena is the next large European X-ray observatory, which will fly in the early 2030s. And one of the instruments on Athena is the Wide Field Imager, or WFI. And this instrument is really built for deep, wide surveys, as its name may imply. The Wide Field Imager, one of the detectors on it is a large area detector, which is an array of active depth pixels. And this detector is, again, it's a large field of view, 40 arc minutes on a side with a PSF of about 5 arc seconds and a fairly short frame time of 5 milliseconds. That's actually an important thing to remember for the remainder of our talks. So among the very interesting science that the WFI will do are two things that we want to talk about today. The first one is mapping cosmic structures through time. And in this regard, it will detect distant groups and clusters and characterize them, as well as characterizing the very faint outer regions of more nearby clusters. And this requires a low known background. So we're not going to talk about the science of this exactly, but we're going to talk about the background and how we deal with that to address this science. And then while WFI is doing these very deep surveys, of course, things go bang in the universe, and produce transients. And there will be lots of transients returned by WFI. And so we'll talk a little bit about that as well. Over here on the right, this is an image produced by the WFI team. This is a simulated 100 kilosecond image of the entire WFI field of view, single pointing, which shows the wealth of distant AGN and groups and clusters of galaxies that will be observed in a fairly modest exposure. So this is a really exciting instrument for doing these deep and wide surveys. Okay, so we're going to present 4 talks today. It's going to be a lightning round of talks. And this is on behalf of the entire US Athena WFI team who I've listed here. And I highlight in magenta the 4 of us that are going to be giving talks. So I'm going to talk a bit about simulations of the background and some ideas we have for mitigating that background. Gerrit's going to talk about validation of those strategies with real data. Dan is going to talk about additional mitigation strategies using machine learning. And then Aman is going to move on and talk about transient event detection. And of course, these are the people who are working on this in the US, but Athena is a European-based mission. So we certainly have to thank the Athena WFI Consortium, along with the Athena WFI Background Working Group, some of the members of which are listed here, who have provided a lot of material that we're presenting today. So I'm going to do a little bit of background about why the WFI background matters before moving into talking about how to mitigate it. Background matters for a couple of things. The first is that it adds statistical uncertainty. If you have lots of events in your X-ray data coming from background, then they swamp out the signal that you're trying to observe. And so one way to mitigate that is simply to minimize the background as much as possible, reduce the number of events coming from that background. Background also adds systematic uncertainty. If you don't know exactly what the background level is, then there is an uncertainty there that cannot be simply reduced by increasing the exposure time. And the way to get around that is to maximize your knowledge of the residual background, understand what that systematic uncertainty is. So we're addressing both of those things in the background projects that we're doing. Now, when I talk about background here, I'm talking about the particle background, and this is primarily due to galactic cosmic rays. They're the primary source of the quiescent background at energies greater than 1 keV for Athena in its orbit, which is nominally L1. These cosmic rays are modulated by the heliomagnetic field. And so the flux of the cosmic ray changes as a result of changes in solar activity. And the timescales on which this happens are manifold. So over here on the right, this is a plot of the Chandra-ACIS high energy reject rate. This was prepared by Catherine Grant, and this covers the entire span of the mission. So this is real data. And so the high energy reject rate is a proxy for the particle rate. And you can see that there are variations on lots of different timescales. You can clearly see the secular trend, which follows the 11-year solar cycle very well. But there's variations, and this is about a factor of 2 variation. There's variations of up to 50%, but even down to 5% on timescales of months, weeks, and even days. And it's important to note that the current requirement for the WFI background knowledge in order to meet its science goals for these really deep cluster surveys is 2%. And so you need to know that the background in your observation is not 2% different from whatever observation you use to measure the background. Otherwise, you do not meet this requirement. And so these 5–10% variations are well above that requirement. Okay, so this is what's motivated us and the Athena team to try to understand what the background will look like. So this builds on a really substantial effort by the Athena team, most of which has been under the auspices of this thing called Arembus to understand, model the background. And this has involved analysis of existing data, characterization of the expected environment, especially optimization and validation of simulation tools, which we rely on heavily. So there are lots of publications. If you go to this reference, which I will show at the end, you can find all of the references from Arembus in there. So in addition, Athena has set up background working groups for both instruments, the WFI and the XIFU, to run these GN4 simulations to inform the design of the instruments and also study other parts of the background beyond just the cosmic ray particle background. So the US team efforts has been really focused not on informing the design of the instrument, but on understanding correlations that we can measure and exploit to reduce and mitigate the background. And so that's what 3 of us will be talking about today for the background. Okay, and I have a list again of references here. I'll show a slide at the end that you can go back to the YouTube video if you actually want to find out what those are. So this is a sort of image I want you to have in your head about what the particle background looks like. Now this is real data from Chandra-ACIS BICCD, and each frame you're seeing in this movie is a 3.3 second full frame. Every little white splotch you see in here essentially is produced by a particle, not by a focused X-ray. And so this is, again, the kind of picture I want you to have in your head. The WFI will also take similar frames to this. Instead of being 3.3 seconds, they'll be 5 milliseconds, so almost 1,000 times shorter. But you'll still have these variety of particle signatures where you have these very long cosmic ray trails, like there's one right there. But you can see mingled in there are these very small signals as well. The very long cosmic ray trails are easy to identify. In fact, these events from those get rejected on board. They don't end up in your unrejected background that ends up in your the data that you're trying to analyze. But the very small things do, and those are the things that we're trying to reduce and understand in the WFI simulations. Now, ACIS and Chandra only telemeter the things that it thinks on board are real X-rays. If we have access to a lot more information, there are probably correlations we can exploit. And so what we've done here in cooperation with our European colleagues is to run GN4 simulations of particles interacting with the WFI and seeing what kind of signal they produce in the detector. So this image down here, this is just a model, a CAD model of the WFI. You can see its housing. This is actually a cutaway, so you can see into it. This blue thing is the detector. And so what our friends at Open University have done for these GN4 simulations is to generate about 100 million protons and then shoot them through the WFI housing and see what happens. And so some of these interact directly with the detector and they produce a particle track. So there's my goofy little animation of a high energy cosmic ray proton zooming through. It plows right through the detector. It leaves one of these long cosmic ray trails, which is really easy to filter out. Some of them, however, do not interact directly with the detector, or rather they interact with the housing of the instrument and produce some secondary particle that then interacts with the detector. And if this secondary particle is an X-ray or an electron and low enough energy, it can produce a valid event, and that is indistinguishable from a celestial X-ray coming from the source that you're studying. So that's what this little blue thing is here. Sometimes the primary itself also produces a particle track, and sometimes, as in the case I'm showing here, it doesn't. Okay. So the upshot of that, or the outcome of that those GM4 simulations, is kind of a rogues gallery of particle interactions with the detector. So I'm just showing 100 of them here, 100 of the million things that interacted. You can see a lot of these are these really long particle tracks, which are easy to remove. There are actually 2 in here, which are unrejected or valid events, and these are indistinguishable from celestial X-rays. There are also some cases where the particle track produces things that look like X-rays in the same frame. Okay, and I don't have time to go into all the details of this, but this is kind of a summary of what we find in these GN4 simulations. And we've divided the primaries into 3 different cases, which you'll hear probably a little bit more in one of the future talks. And so case A is the first goofy animation I showed, where you have a particle track produced, but you do not have a valid event produced by that primary. And this is the overwhelming majority of cosmic rays that interact. 97% of these do not produce a valid event. So in fact, we don't really have to worry about these because these aren't contributing to the unrejected background. The other 2 cases then are where you get a valid event, but no particle track. So that was the second goofy animation I showed. And then the case C is where you get both. You get a particle track and you get a valid event occurring from the same primary. And what's interesting here, these are the cases that we're really interested in. The case where you get a valid event but no particle track actually happens 65% of the time. And so there's no way we can use that particle track information or exploit that and any correlation to remove these valid events, because we don't have information about the particle track from that particular primary. However, for 35% of those events, we do have information about the accompanying primary particle track. And so this is intriguing, because this means if we can somehow associate valid events with their primary particle tracks, we can reduce the background by 35%, which is significant. Now we get about 3 particle tracks per 5 millisecond frame, and compare that to dozens or even hundreds for those movies I showed you from ACES. So we're not actually reading out fast enough to use pure anti-coincidence, because we would end up dumping about 98% of the signal, because we would drop 98% of the frames. But we can exploit this correlation and do something similar. And in fact, what we discovered while we were doing this is that there's a very strong spatial correlation between a particle track and valid events that are produced by the same primary. So I have a little schematic over here, which shows, a number of these particle tracks shown in white. Again, these are easy to filter out. These do not produce any unrejected background. These green things are just schematic ideas of valid events that are produced by those particle tracks. And so if we, for each of these valid events, measure the distance to the nearest particle track, which is shown by these orange arrows, and produce a cumulative probability of that, that's what's being shown in the plot on the right. So this is the thing we call P-core, the cumulative probability of getting a valid event within some radius of a particle track. And I have a bunch of different lines plotted here. Just look at the orange one. I can explain the other ones if anybody has a question. But as a function of this exclusion radius in pixels, this shows the probability of getting a valid event close to a particle track. And you can see that it rises quite rapidly. So even within 100 pixels of a particle track, you have a 10% probability of getting a valid event. And you can also see that this orange line levels off at 35%. And this 1200 pixels radius essentially masks out or removes events from the entire frame whenever there's a particle event. And that makes sense, because only 35% of the valid events are accompanied by a particle track. So we can remove up to 35% of the background in this way. So this spatial correlation is really intriguing, and this is something that we can exploit. The way that we exploit this is by using a technique that we've dubbed self-anti-coincidence. And what you do is, for each of the particle tracks that occur in a frame, you mask around those particle tracks and eliminate any valid events that occur within those masks. And in this way, the WFI becomes its own anti-coincidence detector. It's not pure anti-coincidence. We're doing a sort of partial veto and not dropping the entire frame. But we can exploit this because the size of the mask can then be tuned depending on what your science goals are, depending on how demanding the background reduction is. Now, this requires that all the pixels with signal are telemetered. We need to know where all of these particle tracks are. And so this is something that WFI plans to do, which is different from what previous X-ray imaging missions have done. So I'm showing over on the left here, this is an example 5 millisecond frame that came out of the GIANT4 simulations. So this is real simulated data. And you can see there are a handful of particle tracks in here. All of these white things are particle tracks. This is more than we get in a typical frame, but I just wanted you to be able to see it. And you'll have to take my word for it, but there is in fact an unrejected event right in the middle of that magenta circle. You can't see it because it's just a single pixel, but it's there. So what happens if we do this self-anti-coincidence? And so we choose some region, some exclusion radius around which to mask. So this shows 5 pixels. We're excluding anything any events that happen within 5 pixels of the particle track here, 10 pixels, 20 pixels, you sort of get the idea. We have to get up to 200 pixel exclusion radius before we eliminate that unrejected event. And you can see we've removed about half of the area of that frame. So we're certainly removing signal, but we're also removing unrejected background events. And so you can go as large as you want. So an example I'm showing here is that you can, again, tune this masking depending on your science goals. And so if you're in some regime where you're really heavily background dominated, you can do aggressive masking to convert these systematic background uncertainty errors into statistical ones. And so you end up eliminating signal, you end up eliminating background events also that aren't associated with the particular particle tracks that you're masking around. But because you've reduced the systematic error, you're now able to make up that uncertainty with longer exposure. And so this plot over here shows, the x-axis shows background counts. And I've drawn lines for a couple of different notional surveys. So the orange ones are for sort of modest exposures of 100 kiloseconds. This one is for a small extraction region of 1 square arc second, for a small extraction region of 10 square arc seconds. And I'm plotting on the y-axis the improvement in the signal to noise ratio. The signal to noise ratio here is given by this expression where now we've introduced a systematic background uncertainty sigma, which is not reducible by increasing the exposure time. If sigma is 5%, you follow this green line. And you can see for these modest surveys, it really doesn't help. It hurts you because you're, by masking at 600 pixels around particle tracks, you're eliminating signal much faster than you're eliminating background. But when you get up to a very deep survey of 1.5 megaseconds, especially for a large area where you're heavily background dominated, you can improve your signal to noise by about up to 30%. And so this shows that for a 3% error, the requirement is 2%, but you can sort of extrapolate and see that even for a requirement of 2% uncertainty, systematic uncertainty, you can still increase your signal to noise ratio by adopting this scheme. Okay, that's all I have time to talk about. The takeaways here are that this self-anti-coincidence spatial masking can reduce the systematic error. And the real key here is that it can be tuned. So depending on how background dominated you are, you can increase your masking. You end up removing a lot of signal, but you make up for it with increased exposure time. And you move yourself from the systematic dominated regime to the statistical dominated regime, or you find where that balance is. And if you telemeter all the information, you don't have to do this at all. So if you're only interested in point sources, you use all of the data and you get all of the signal that you need. Okay, so here's a list of references that I mentioned. So please go to the YouTube video and hunt these down if you want. All of this is described in somewhat excruciating detail in a JADIS paper that we have submitted and hopefully come out later this year. So I think it's time to turn over to Gerrit. I'm happy to answer any questions in the chat that you have. So Gerrit, I'm going to stop sharing my screen and why don't you take over?
Wonderful, thank you, Eric. Okay, you're able to see my slide?
Yes, we can. Thanks.
Okay, perfect. Yeah, so I will just pick up where Eric stopped, and I'm gonna talk about the work that I'm doing here at SAO together with Ralph Kraft and Paul Nolson, looking at actual real data from XMM-PN to develop methods and algorithms to mitigate the particle background in general, current and future X-ray missions, but specifically also looking at the Athena WFI background. And we are doing this together with all our collaborators from MIT, Stanford, Penn State, but also with our European colleagues at the in the Athena WFI Background Working Group. So, so just to motivate again, in case you forgot already, so any of these science capabilities of future X-ray missions will be crucially limited by the knowledge of our instrumental background. And clearly the current paradigm of just removing blank sky or local background won't be sufficient for the Athena science goals. And just to illustrate that a little bit and give you a flavor of what we are actually talking about here, I have in the plot on the right side average temperature profiles of galaxy clusters, all normalized, and they are stacked together, put into groups indicated by the different colors here, and the groups mark different thresholds where the background starts to dominate at different levels over the actual source signal. And we clearly notice here that as soon as the background starts to dominate more and more over the signal, not only the uncertainty increases, but there is a bias introduced in the measurements here. And that is destroying any kind of science output that you want to gain out of very low surface brightness regions. So the only way to overcome this is not by taking longer exposures, because the source over background count ratio won't change, but the way to go is to unlimit the background, the instrumental particle background, and reduce and understand where it's coming from and its uncertainties and systematics that are involved in there. So any of these results can not only be applied to Athena, but in general to X-ray missions that are planned currently and might go forward in the future, such as LYNX or AXIS. So in general, this goes far beyond any efforts that have been done previously with Chandra and XMM. And how we want to tackle this is by looking at the PN small window mode camera specifically, because this is a huge data set that has been recorded in the archive, typically between XMM slews from science target to science target. And it allows us to study the relationship between charged particle events and that are usually filtered out by the onboard processing, and events that are telemetred to the ground in regular full frame observations, for example. So this small window mode is very helpful because not only it has a small frame time very similar to Athena WFI, but Athena will also provide these capabilities of transmitting all the data to the ground, even the particle events that are usually rejected due to either their pattern distribution or their pulse height that they imprint in the data set. So these are then things that can be compared. The results we draw from the small window mode data can be compared directly with anything that comes out of simulations. And with that, we can actually validate any results that can be drawn from these simulations. So what I'm actually talking about, maybe that becomes a bit more clear looking at these two spectra that come from the XMM PN instrument. And the orange one is full frame mode data, so some science mode that is usually used for observations, and the small window mode in blue. And you clearly see that at the higher energies, you have a cutoff at around 15 or 16 keV in the full frame mode data, while you have all the data of the particle background still in the small window mode data, which leaves this large peak at the largest energies. And this is actually what we are interested in, because these particle events basically tell us something on the relationship, what particles or what events are still left in the usual data. So to understand that better, let me first explain the actual PN camera in just one slide quickly. So we have 12 CCDs that are in the PN camera arranged in 4 quadrants, and the small window mode just picks out this small little square in the middle here of CCD4. And this is all the data that we are working is from this little window over here. But there are several similarities in the WFI and PN camera. So the pixel size is roughly comparable. Both detectors have a relatively thick depletion depth. And of course, as Eric mentioned, the frame time is very similar. So that is very helpful if we want to draw any conclusions from the small window mode later on to the WFI predictions. So the data is recorded in frames typically, and in the small window mode, we can subdivide the frames into the 3 categories that Eric already mentioned. We have the frames where we only have particle events, so something that is removed usually by the onboard processing. And in case B, we have X-ray-like events, something that is typically just a single pixel or a very small pattern. And then the case C events, frames that have both particle track and an X-ray event. And while all of these are very interesting to study and important to understand, the specific attention is to be drawn on the KC frames, because there we can have in the same frame an X-ray-like event that we usually associate with the particle track that is in the same frame. And we can then draw conclusions on if that's a genuine X-ray or some secondary or other particle-induced event here. For example, as Eric already pointed out, the self-anti-coincidence method helps us with that. And this has been published already in the past by Ezra Bulbul, looking at a little smaller data set in a narrower energy window. But already this showed us a great result by looking at the distribution of the distances between these genuine X-ray events and the particle tracks. And if we compare that with an uncorrelated distribution, something that we would expect if those events were completely independent, we see that there is a huge access to the smaller distances. That means the closer these 2 events are, the more they are related to each other. So if we try to remove them, something that Eric already showed with the increasing distance, we can significantly reduce the particle background already by 10%. And this is just in this harder energy band. So of course, we want to go much deeper on that and not only expand the band to the full energy band and have the full potential, but that also brings up new challenges. We want to understand its variabilities in terms of long and short term or spectral variabilities. And of course, looking just at the particle tracks, this can also help us to just get an understanding of the simulations. Since we have a lot of these particle tracks in the small window mode data, we can understand its distributions and properties. So how do we do that? We look at these case A frames and try to characterize these particle tracks. And I show you here a few of those. And we parameterize them by putting a simple box around those particle tracks that we see in individual frames. And then we can define something like the elongation, the orientation angle, or just simply the location where is the center of this particle tracks with respect to the overall detector. And we study these properties, and I just want to pick out 3 right now and look at those a little bit more closely. So on the left side, you see here in this 2-dimensional histogram, just the distribution of these particle track islands. And you see that there are many more on the right side, which is further away from the readout electronics than on the left side. So there is, if you parameterize that, or if you fit this gradient, you see that there is a 33% increase over the whole detector of this small window mode. So how can we understand that? Why should be on one side more particles than on the other if they are uniformly coming to the detector? So to understand this, we want to look at the readout mode, how actually the small window mode data is read out. And after the actual integration that you see here, the frame is shifted down to the readout area. and then slowly read out row by row. And in each, and the last row is having more exposure to the actual particle background than the first one that is read out. So that means that there is a variable exposure map across the detector for the particle background, which seems to have exactly the same dependence as what we see here, which means a 33% increase in exposure from one side to the other side of the detector. So these small subtleties already tell you that if we understand our detector very well, we can understand the particle background better and in the future also reduce the impact of it. Other properties that are worth looking at is, for example, the orientation angle of these particle tracks, which seem to be fairly uniformly distributed, or the length distribution, how elongated are they? So obviously we have more shorter tracks when the particles just go right through the detector, or if they go perpendicular to the detector plane, we have longer tracks. Does that fit our expectations, the distribution? Well, we can just compare that and assuming the detector as a three-dimensional box with a constant particle flux from all sides. And this gives us a prediction on what we expect as the particle, as the length distribution of these particles is shown in this black curve over here. The orange histogram or red histogram over here gives the actual observations that we got by filtering out the edges around the small window mode. And we see that there is a clear mismatch between the simple expectation from this box model to what we actually measure. So maybe there is an additional population of particles that leave a different imprint. Or could we be missing longer particles because they might, some of the particles might be stopped when they go through the detector. But clearly this is not the case for galactic cosmic rays because they have a much higher energy than what is required that they get stopped by going through a silicon detector. So this is something we are still currently investigating, but I think the direction is very promising here, and the results might really help us to reduce the level of the background and understand how it is actually composed. So I just leave here the conclusions, and what I've been talking about was to motivate the importance of the small window mode to investigate and basically verify all conclusions drawn from simulations. The self-anti-coincidence method has already shown its success for a smaller band, and we want to expand on that, but also look at the particle properties. For example, its 2D distribution or length distributions can help us to really verify if we compare that with simulations. Are we going here in the right direction, or are we missing something fundamental in the understanding of how the detector locates these particle tracks? If we go to a wider energy band, we might also get the spectral behavior of these components, especially once we go to filter wheel open data, where we have not only the particle background recorded, but also we see a different background components such as the soft protons, which leave a different spectral imprint on the detector, and we might be able to filter that out once we explore the full band. And I will stop here and hand it over to Dan.
Hey, thank you, Gerrit. It's a great pleasure to be able to join you today to tell you a little bit about the work we've been doing at Stanford in collaboration with the WFI team, particularly the US WFI team, to find out if we can use machine learning approaches to maybe help tackle this problem of reducing the particle background in the Athena WFI and in other X-ray imaging detectors. So just as a very quick recap from what Eric said, what we're talking about here are the background signals that are produced in our silicon detector. And we're trying to separate those out from what I'm going to call astrophysical X-rays. So these are the real X-rays coming from the sky that we want to detect. We need to separate those out from the signals that either arise from cosmic ray primary protons that either go straight through the detector, leaving a track, or from a cosmic ray proton that interacts with some other part of the instrument or the spacecraft and then produces a shower of secondaries, including X-ray photons and electrons that then interact with the detector. And for the purposes of this talk, when we have a shower of secondaries, I'm going to consider a single cosmic ray event as being everything that's produced by a single primary. So that will include all of the secondaries that come from one proton interaction. And the way we typically filter out these events in the current X-ray data is by looking at the energy that's deposited in each pixel in the event, and by the pattern of the pixels illuminated by an event. That pattern is also known as the event grade. So the valid X-ray events are single or double pixel, maybe quadruple pixel if you've got a small detector pixel size, and have energies less than approximately 10 keV, the energy that we expect to be able to be focused by the mirror. So these are the valid X-ray signals we're looking for. Then we have these proton tracks that are very clearly invalid events. These are very clearly produced by cosmic rays traversing the detector, and can be readily thrown out either based on just the shape of the track, or if the energy in the pixel is more than the threshold. And then Gerrit showed that the XMM filtering was cutting off events above about 15 keV or so. But then we have these interesting cases. What if we've got a valid event that's next to a particle track? Is this a genuine X-ray photon from the sky, or is this a secondary that's come off of that particle track? Is it a fluorescence photon that was produced by the interaction of the proton with the spacecraft, or is it an electron? Electrons look just like photons when they are absorbed in a pixel. So the goal of our work has really been to better try and characterize these events. So come up with new methods that can actually associate secondaries such as this with their primaries, and let us reliably detect and reject these background events that might look like valid events. So the approach we've been experimenting with has been that of machine learning, in particular using image classification algorithms that are based on convolutional neural networks. So the idea here is we take the image that's produced in a single frame from the detector. So that's the charge that's deposited in all of the pixels in a single frame that is read out of the detector. And we train these machine learning algorithms to look at all of the pixels in that entire frame, everything that could be due to valid photons, particle tracks, and secondaries. Just look at the whole frame together. And then we want the algorithm to tell us how we can optimally divide up those signals we see into the different events, and then classify those events as being genuine X-rays or background events that are due to being charged particles. So the sort of idea we might have here, that the first simple thing we can do is we can just look at this whole frame and we can ask the algorithm to tell us, does this frame only contain X-rays? Does it contain only cosmic rays, or does it contain both? So what we'll do is we'll have the algorithm look at this whole frame, and it'll see this cluster of signals, the track, and this maybe valid event next to it. And then it will, and then there's this other event here. And we'll have the algorithm look at this whole frame, and it will assign us a probability that tells us what's the chance that this frame contains X-rays, cosmic rays, or both. So just in this cartoon example here, we might have the algorithm say, well, there's a 91% chance this frame contains both, given this isolated valid event here, and then a small chance that it's only X-rays and only cosmic rays. And then we want to drill down further into this. And we actually want the algorithm to tell us, okay, which pixels do we want to include in our analysis as valid events? So in this case, the algorithm will identify the individual events within the frame and then tell us the probability that it is produced by a cosmic ray. So it might look at this whole collection of pixels here and say, okay, this valid event is close to this track, so I'm going to group all of this together, and it's got a 99% chance of being a background event, so the observer can reject that from their analysis. But then this event here is far enough away that it's only got maybe a 7% chance in this stupid example I just drew as a cartoon, so that we might want to include that in our analysis. All machine learning algorithms require training data, and we generated these training data from the GANT4 simulations that Eric talked about. So we trained this algorithm on a number of simulated frames that contain some random combination of X-ray photons and cosmic ray events. But the really important thing here is that the frame time of the Athena WFI is so fast that the number of events we get per frame is always very small, which means it's easier for machine learning algorithms to disentangle cosmic rays and photons than it would be if we had a long exposure time and lots of events together in the same frame. So here's just a couple of the example of the training set we've got. And of course, for each of this training set, we know the truth. We know which pixels contain cosmic rays, which pixels contain X-rays. So that can be used to train the machine learning algorithm. And then we can take another pristine set of frames that the algorithm has never seen before, and we can verify the performance. So just thinking about the neural network algorithm, first of all, that just looks at that whole frame and tells us what's in the frame. What we have here are input frames with X-rays only, cosmic rays only, cosmic rays and X-rays, and multiple cosmic rays. And these bars show the fraction of those frames that are classified as either having X-rays only in blue, the fraction of them that are shown as having cosmic rays only in red and having both in green. And we can see that for each of these categories, that in the vast majority of cases, the algorithm is making the correct decision. And something like 99% of the cosmic rays are being successfully identified, and our false positive rate is low. However, what we really care about, though, is how much better can we do than the old-fashioned event pattern plus energy framing, because that's also very effective. It's 98 to 99% effective on the GANT4 frame. So we really want to know how much we can improve the background. So this is a promising first step. We can also look at those events that look like they're valid. So the X-rays, the fluorescence photons produced by the cosmic rays, and the electron and positron events that look just like photons when they interact with the silicon detector. And it turns out that although these are hard to detect in isolation, if you just have one electron in a frame, or you just have a fluorescence photon in a frame, but if these events come with other events, if they come with a particle track, we can successfully identify them. So this is machine learning how to do the self-anti-coincidence that Eric talked about, and working out what the length scale that we need to cut on is. The other thing that machine learning is able to do is it's able to identify secondary photons and electrons, even when they don't come with a particle track. It can do that if we have multiple of these events in a frame. So even though there might be no track, if we have a nearby cluster of electrons and photons coming together, if we have too many valid signals coming together in a short readout frame, that this can't be X-rays coming from the sky because there's too many of them, the machine learning algorithm is also able to identify those as being cosmic ray induced events. Then we want to extend our algorithm to not just tell us what's in the frame, we want to tell us which pixels are the background events in. I mean, I'm not going to go into any details on this because I don't really have the time, but I'm happy to answer any questions or talk with people offline if you're interested in this. But we can create a machine learning algorithm called a UNet that essentially uses a convolutional neural network to identify what's in the frame, called encoding, and then it picks apart the decisions it made in the convolutional neural network. It works backwards through this what's called a decoder to actually assign those identifications to the individual pixels. And this means if we have a frame with, say, some particle tracks and an X-ray photon, or some particle events and a photon here, we can then assign the probability of each pixel having a photon in it or having cosmic rays in it. So this is the algorithm showing us where the cosmic ray induced events are in these test frames. We then add this column to the event list, so the observer can decide their rejection threshold. They can choose the probability assigned by the neural network above which they reject an event. And we actually find that a probability assigned above 10% actually works very well here. We can keep the signal loss to less than about 10%. We can reject less than about 10% of the valid X-rays while catching most of the cosmic ray-induced events, even with quite a low rejection threshold here. And we find, just by comparing the background spectrum we expect using the old-fashioned grade and energy or pattern and energy criteria that's shown as the blue spectrum here, comparing that to the background spectrum we get after filtering with the AI algorithm shown by the orange spectrum here, we find that we're able to reduce the background in these very early simulations. So these aren't completely realistic simulations of the detector and how this algorithm would work, but this is at least a feasibility test showing us that we think we can at least get this background down in the 0.3 to 10 keV range by about 27%. So this is telling us that we think we're kind of looking in the right direction for using machine learning to reduce the background. So our big takeaway from this is that neural networks and machine learning are providing a really promising route to reducing the particle background, using the spatial correlations between events in a frame. That's what the neural network is learning. And before I hand over to Aman, I just want to say very quickly, if there's any grad students or postdocs on the job market and using machine learning and new methods of detecting background in X-ray detectors sound interesting, we actually have an opening for a postdoc between Stanford and MIT, and the advert is on the job register at the moment. So I will hand over to Aman.
Thanks, Dan, and thanks to everyone for inviting all of us. And this is Amanpreet Kaur, and I'm giving this talk on behalf of A. Falcone and Dave Burrows from Penn State University. I'm going to switch the gears here a little bit from WFI background to monitoring transients with Athena WFI, and basically focus on finding neutrinos from using Athena WFI. So just starting from the very basics, what are the main goals for this X-ray instrument? It's to understand the hot and energetic universe, study of clusters and galaxies and how are they formed, their chemical environments and the evolution with time, basically looking into the deep X-ray universe. And the other very interesting phenomena, physics of accretion onto compact objects, which we basically see a lot in X-ray astronomy. So that's another thing that Athena is going to look for. So what is different from the existing instruments in this one? One main thing is the effective area as well as the sensitivity. So here, what you see here is a plot of energy versus the effective area for this particular telescope as compared to XMM as well as Chandra. So you see that it has a rather large effective area as compared to these two instruments, and also the sensitivity is 10 to the minus 17 ergs per centimeter square per second, which is one of the deepest X-ray, which is great for deep X-ray astronomy exploration. Okay, so since we are going to talk about transients, so I'm going to throw in some buzzwords here. So basically, what do we mean? What kind of transients we are mainly interested in from the X-ray point of view? So coming ultraluminous X-ray sources, tidal disruption events, gamma ray bursts, neutrinos, fast radio bursts, fast X-ray transients, active galactic nuclei. And this list doesn't really end here, but just kind of focusing on that, what are the main things that we can study or look at. A lot of these events, we understand physics behind them very well, and for some of them we don't. So these are the objects that we are going to explore. So right now, let me just focus on 3 or 4 such sources and see, like, for example, what we are seeing right now is with the current X-ray telescopes versus what a WFI is going to detect. So for example, the first one, what we're seeing is of a tidal disruption event. 2020 basically laid out this whole publication, which discusses like what are the various kind of transients we can detect with WFI and what will be the rate of all those events per year that we will see with Athena based on certain assumptions, such as like what is the known outburst rate, what is their number density, or like what is the typical flux, using all that information. So I'm just basically tabulating here some of them. Like, for example, you can see that for example, like SDSS, this particular object, you can see about 75 of them using WFI in a year, which is quite substantial, as well as a rare ULX in M82, which typically you would find 1 in a galaxy, or maybe sometimes you don't even see anything. So the probability is approximately 1 again using WFI. And then blazars like Markarian 421, which is highly variable. Blazars in general are very variable over a couple of minutes to like hours and days. But for Markarian 421, which is very variable and very well studied, so you would see a blazar like that, approximately 3 of them using this particular instrument. And then the next 2 are quite interesting and new in astronomy. So the fast radio bursts. So we don't really have any X-ray detection, but this particular FRB 121102 was studied simultaneously using Chandra and other instruments. And so using the upper limit for in terms of X-ray, so actually you can detect more than thousands of such sources with this particular instrument again. So that would give us a great sample size to actually look at this kind of source class. And last but not the least is something very interesting. So these are the fast X-ray transients, and unfortunately we don't know much about their nature, like what is the physics that goes behind them. And there are 4 known, and all 4 of them have very different behavior, like looking at the light curve and how they show flares. So there is a probability of detecting approximately 2 of this kind that I'm showing here. And then the same thing for the other 3 that are there. So this is a very brief overview, but to get into all the details of this, one should definitely look at this paper. It's very thoroughly written. So then let me just go a little bit into the details of some of these transients. Like, for example, the last one that we were talking about, these are the fast X-ray transients. So what exactly are these? Like, for example, here, what you see in this figure on the right-hand side, that this was found in Chandra archive. And what was seen is that there was this really rise in the counts from 0 to approximately 20, and then it decayed down to almost 1 counts per second, and then it again went up to about 20, 30 counts in 10 seconds, and then it decayed down. So this time scale is really tiny, that about few seconds. And that's very important, for example, in Athena, due to its sensitivity. And so we will be able to detect sources like this a lot with really short time flares. So finding sources of this kind would be a big plus with this kind of instrument. So this is one of the topic that one of the source class that Athena will definitely be great at looking at. So there are no good explanations of these sources, but like, for example, there are different theories out there, like could be tidal disruption events, or a white dwarf and an intermediate mass black hole involved in the system, or some gamma ray bursts, which are off axis. Something like, there are a lot of theories out there for these kind of transients, but none of them explain really well what is going on here. Okay, and this is one example of such. And the next one we're looking at is something fast radio bursts. And the first one was detected in 2006, which actually came from data taken in 2001 from a pulsar survey for Magellanic Clouds. And these flares were for milliseconds. And for example, for this particular source that you see here, this was the very first one, and you see this flare, which is for a very tiny amount of time. But then, so this was witnessed for the first time, and again, there was no explanation of what was going on. So after this source, there have been, I think, more than 100 sources. Approximately, some of them do show outbursts which are repeated, but some of them are just like transients, that you see this one flare and you don't see anything else at all. The only caveat here is that we don't know any X-ray detection so far. So that's one thing, but maybe with the better sensitivity with Athena, we can actually have X-ray detection as well and have more multi-wavelength point of view to understand what is going on in this class of objects. Okay. And then neutrinos. So basically what is happening is, yeah, we are not exactly looking for neutrinos directly with Athena X-rays. So, but we are going to study source classes to see if they are the source of neutrinos. We all understand that cosmic rays are produced in extreme environment, and neutrinos are produced in these fields. So cosmic rays are deflected by magnetic fields, whereas neutrinos, they barely interact with anything and they travel really straight to us. So studying cosmic rays directly is really hard, whereas neutrinos we can easily study because we can recreate the direction they're coming from. Whereas with cosmic rays, because of all this deflection, it gets really hard. So studying neutrinos would provide us indirectly the information about the cosmic rays origin. And so far, blazars, supernovae, all these high energy phenomena, these are the possible sources for these neutrinos. And in the relevance of this talk, what we're going to do is we're going to focus on one such source class called blazars, which is one of the possible known sources for producing neutrinos. Just a short introduction. Blazars are active dielectric nuclei with their jets pointing along the observer's line of sight. They possibly produce neutrinos by hadronic mechanisms, proton-photon interactions, creating pions which decay into muons as well as neutrinos, some of which travel directly to us and then we see them. So basically this is an active galactic nuclei and the torus and the jet, and we would be sitting in the direction of this jet, and that would be a blazar. So why we are focusing on blazar basically? So a few years ago, what happened was that in 2017, September 22, there was a blazar TXS 0506 plus 056, and a high energy neutrino, which was about few hundred TeV energy. It was detected at Ice Cube Observatory. And what was found that the direction of that neutrino coincided with the direction of this blazar. And Fermi, which is a gamma ray telescope, as well as MAGIC, they were also witnessing flaring in the gamma rays from this particular blazar. So there was a correlation, possible correlation that was going on with the detection of this neutrino as well as the flaring of this particular blazar. So various X-ray telescopes and so other many multi-wavelength observations for this particular source happened. And the studies of gamma rays as well as the neutrino from this particular direction, a correlation, it was found that the correlation between this gamma rays as the neutrino as well as this neutrino were statistically significant at about 3 sigma level. So basically it was shown that there is a high chance that this neutrino is related to this particular blazar. And so that's why since then, I mean, it was always in theory predicted that blazars do produce neutrinos, but there was no observations as such. And this is the best result we have so far, statistically speaking. And so this is another chance that has given us that, okay, we should definitely explore blazars more for finding neutrinos from the sky. So this is a table that you're seeing here, which is basically multi-wavelength observations. There is a lot of stuff on it. So let me just walk you through it. So on the x-axis, you see the time in the modified Julian date. And on the y-axis, what you're seeing is mostly flux, except one spectral index information for different observatories, starting from high energy to low energy. So it's MAGIC, Fermi, Swift, and optical telescopes and the radio telescope. So these are the light curves, long-term light curves for this particular source, TXS0506. And the right side is more zoomed towards the time when this neutrino was detected. As you can see, like for example, in Fermi, there was a little flare that was detected before neutrino was detected. This dashed line corresponds to neutrinos detection time, and as well as MAGIC, it had some flaring activity a little after that, and Swift had some flaring after that as well. So as I said earlier, that there was something going on the gamma ray sides and this on the higher energy side for this blazar when that neutrino was detected. And what you're seeing here is the light curve that we extracted using Swift data that we have for this particular blazar. And what we noticed is that, like, for example, here you see the flux as well as MJD, and this is all the information that, all the data that we have for TXS0506 with Swift. And the blue data points are the one now which were taken very close to the neutrino detection. And this one, which has a little round around it or circle around it, is the one immediately taken after neutrino detection. And these blue data points correspond to a time span of about 10 days. And in those 10 days, the flux changed by a magnitude of about 600, by a scale of 600. So, which is quite a lot. Markarian 421 has never shown this so far, although it's very well studied or any other source we know of. And then we looked at a paper by Okunomo in 2019. So they actually looked at different kind of models for different blazars, including TXS0506, and they predicted that you would only see about 10 to the minus 2 neutrinos coming from this particular source. So there is a little discrepancy between theoretical prediction versus what we have seen so far. So we really need to understand blazars a lot more, as well as like how neutrinos are produced from these blazars. But this was a good data to check that, you know, if the flux rises in such a small time by such a large amount, that could be a way to look for neutrinos. And that's what we would want to do with Athena. So Athena's role, again, coming back to that slide, is that sensitivity is 10 to the minus 17. And it has the capability of detecting really short flares. So this will be perfect for looking at blazars for these small flares, but then really big change in flux. And that would be something we can do to look for neutrinos. And when we see this kind of flare, and then doing the data analysis and everything, send out that information to networks such as AMON, and then trigger the multi-wavelength facilities, that would be ideal, because what we really need is something that should happen within few hours, if not like few minutes instead of like a couple of days or months. Again, for this, just towards the end of the talk, I would like to point out that for the same particular source, prior to the 2017 observations, IceCube collaboration, they went into old data for this particular source, and they noticed that there was a lot of neutrino production. They found 13 events during this time, 2015, in the direction of TXSO 506. And possibly we could have detected a neutrino at that time with a higher statistical significance. But unfortunately, we didn't have any observations at that time with Swift. So what you are seeing here is again all the Swift data we have. This is in 2017 and onwards, and before that we barely had any information at all. So this would be a great project to look at. So in my concluding remarks, I would say that Athena, with its great sensitivity, is ideal for detecting transients with large number as compared to what we have right now. And then probability of finding a blazar in Athena's field of view while it is observing targets such as galaxies cluster is relatively high. So we are not saying that we want to target these particular blazars. Athena has a large field of view, and while it is looking at something which is the main primary target, there is a probability we'll see a blazar there, but there are many thousands of blazars in the sky. So if Athena is taking data and we see this flare, so we would inform networks like AMON and trigger other multi-wavelength facilities to take all these observations, and that would serve our purpose, and then look for neutrino detections and conduct the science. Thank you. That's all I have.
Thank you very much, all of you, for this great succession of impressive talks and results, and looking forward to see all this working on Athena. So there was a question, a double question by Brandon in the chat, but I saw Eric answer the first one, and I think also the second one.
Yes, I gave a double answer, but I'm happy to clarify if need be.
So if Brandon has...
Sorry, I was on mute. Yeah, no, I think that answers what I was asking. Thank you so much.
Yeah, I completely skipped over the input galactic cosmic ray spectrum just because of time. But yeah, if you go to that Erard's or probably any of those references, it'll certainly point you to a reference where it describes the input galactic cosmic ray spectrum. But the solar min was chosen both because Athena was thought to be launching or might have been launching around solar min, which means that there's the least shielding of galactic cosmic rays, so the background would be highest. It's also a conservative case. And there certainly was some analysis about the differences between solar min and solar max, but there's not really sort of a fine-grained analysis of what happens due to variability on those really small day-week burblings that I showed. So that's something that we are currently at MIT have embarked on right now, using in situ data, especially from the atomic mass spectrometer and things like PAMELA, which actually see these variations in the galactic cosmic ray flux, and tying that to both Chandra and XMM variability to see if we see what kind of variations we see in the unrejected background. So that's ongoing, and that will be very important, I think, because the requirement is a 2% knowledge of the background, and so if your background observation is separated by days or weeks from your science observation, you need to know exactly how different it is at the level of 2%. So.
Thank you. I would add also an aspect that the last solar minimum, not all solar minima are the same. The last one was particularly very weak, probably the weakest on record. This implies that the testing we are doing now is probing regimes of galactic cosmic ray flux highest than ever. So you are probably in the worst possible situation, which in fact can turn out to be good for a better testing of the instruments.
Yes, yeah, I think that's right. And of course, the solar cycle, as you just implied, is not is not the same from cycle to cycle. So who knows what it'll actually look like when Athena launches.
Is there any other question? I thank everybody to stay here so long. Today it lasted a little bit longer than usual. I don't see hands raised. I don't see anything in the chat. I just would like to add that while people think more about possible question, that we still have the spreadsheet for appointments. There are still a few slots available. The spreadsheet collects all emails of all 4 speakers. So if you don't see time slots for the specific speaker you would like to speak to, there is an email, so you can contact the speaker directly to schedule an appointment. I don't see anything at the moment.
If you don't mind, I could ask a follow-up question really quick about plans to include a charge transport model or things of that sort. Is that a area of active activity, or is that something that you don't view as a very big value add in your models?
No, I think it is a big value add. So we've actually been working on this for other purposes. So we have a framework in place to simulate charge diffusion in detectors, and our plan is to incorporate that basically as sort of post-processing of the GM4 data, along with Dan and the folks at Stanford, because and Dan can certainly say more about this, but my impression is that the AI training set needs to be as high fidelity as possible, because AI is pretty good at picking out patterns that are introduced by accident. So I think you really want the training set to be as realistic as possible, and so including the charge diffusion and other charge transport is pretty important. But I don't know if you have anything else to say about that, Dan.
Yeah, that's correct, because I think the most interesting case for the AI is detecting not the clear particle tracks. It's the small patterns that look like valid X-ray photons. When we really care about the difference between a 2-pixel, 3-pixel, 4-pixel, 5-pixel event. So a realistic model of charge diffusion will be really important there. Just sort of backing up what Eric said, the reason we haven't, the initial data didn't do that is because while we sort of understand charge diffusion for X-ray photons, where all the energy is deposited at a single point in the detector, it's a little more complicated of how to apply that to particles that travel through the detector. But it's something that we're definitely working on, and Eric and the MIT team are really leading that with the charge diffusion code. So watch this space.
Thanks. Sorry for dragging out the session longer. I guess I'll have to sign up and bend some people's ears longer.
Sounds good.
All right. So I don't see other hands raised or questions. So let's close today, this moment, and we'll see you all next week. Thank you.
Great. Thank you very much.